Okay, so one more of these videos where I show you how I read math. Now we're in the same page as before, page 157, section 6.3 in Mileti's book, 157 right there, which you can look it up. And now we want to do these things. So it says, we can now use compactness theorem to show that certain elementary classes are not strong elementary classes. Again, you look it up. Strong elementary classes means that they are a set of models of some finite set of sentences, or equivalently, a set of models of a single sentence, because you can put ands between them and get a single sentence. So this is saying a certain something that we know is elementary. So it's a class of models of some set of sentences, but not of a finite set of sentences. The key result behind such arguments is the following proposition, which says that if you have a strong elementary class K that we already know is equals the class of models of some sigma, then for some infinite set sigma, then we can find a finite subset of sigma itself witnessing the fact that K is a strong elementary class. So it's saying what the proposition says, so if you read the proposition it should say the same thing. Suppose that K is a strong elementary class, sigma is a set of sentences in some vocabulary L, and K is the class of models of sigma, that's what we are saying. Then there exists a finite sigma 0, including sigma, such that K is a model of sigma 0. Okay, so here, why is it not like what it's saying? Why does it say that what we said before? Here it says that if we know that the K is a strongly elementary class, which means we know that it's the class of models of some finite set of sentences. And then here, well, the conclusion is that it is a class of models of a finite set of sentences, sigma 0. So when you see this, be like, stop and be like, okay, wait, what is it saying? Well, what we know is that it's the class of models of some finite set of sentences, but we don't know that this finite set of sentences need to be a subset of sigma. Okay? So that's the new part about this. So we know it's a model of a finite set of sigmas, but we didn't know sentences, but we didn't know that we can always choose that finite set to be a subset of sigma if we know that K is a class of models of this big sigma. So that means there could be many finite set of sentences that axiomatize K, but what it's saying is that if there is such a finite set, there must be one that is a finite set of this sigma. Okay, and that's gonna be useful because that means that if we have sigma for K, then and we know that it's strong, and we want to prove that it's not strongly elementary. So that means if we assume that it's strongly elementary, it has to be axiomatized by a finite subset of those, and not by maybe some other formula that we cannot control, as we're going to see in the example afterwards. Okay, so let's look at the proof of this proposition. Since K is a strong elementary class, we may fix tau. Tau here is a sentence. Okay, so sentence tau such that K is a set of models of tau. And in principle, this tau has nothing to do with sigma. But we know that we then have that sigma semantically implies tau, or logically implies tau, that's what we call it. Because any model of sigma is an element of mod sigma. That's what mod sigma means, which is the same as K, that's what we assume, and it's the same as the models of tau, and hence it's a model of tau. So, okay, so let's read this again. So we want to be saying that sigma logically implies tau, and what does that mean? That means every model of sigma is a model of tau, and that's because every model of sigma is a model of tau, because models of sigma is the same as K, is the same as models of tau. Okay, so every model of sigma is a model of tau. Good. Therefore, by compactness, and by compactness here, okay, let's finish reading. We may have we might fix a finite subset sigma 0 of sigma such that sigma 0 already implies tau. So we know that sigma implies tau, and now we're taking a finite subset that implies tau. We are using this form of compactness that says that if whole set logically implies phi, then there has to be a finite subset that already logically implies phi. That was another version of compactness that we're using. Okay, so we have that this finite subset implies tau, and then notice that K is class of modulus of sigma is a subset of a class of modulus of tau, of sigma 0. Why is that? Well, because sigma 0 is a subset of sigma, so if you're a model of everything in sigma, you must be a model of the ones in sigma 0, which are fewer. So it's easier to be a model of all of sigma 0 than it is to be a model of all of sigma, which is a larger set. So you get this inclusion. And the models of sigma 0 are including the models of tau. Why is that? Well, because sigma 0 implies tau. So if you're a model of sigma 0, you are a model of tau. So that's why that inclusion. That is K. So we got that this, then it says, then K is a model of sigma 0. Why is that? Well, because K is included in the models of sigma 0, and sigma 0 is included in the models of K, so you get they are the same. And that's it. Yes, that's it, because we got sigma 0 is a subset of sigma, and it's finite, and its models are exactly K. Cool. Okay, so that's the proof, and let's see how you apply this proposition. Corollary. The class K of all fields of characteristic 0 is an elementary class, but not a strong elementary class in the ring theory language or vocabulary. 0, 1, plus, minus, and times. Okay, so if you don't remember your abstract algebra, you can look it up in Wikipedia. Let's say what's a field, and essentially a field is a ring where every element has an inverse except for 0. And what is the mean having characteristic 0? Characteristic of a field is given as follows. If you take the element 1, you add it with itself, 1 plus 1 plus 1 plus 1 plus 1 plus 1. If eventually you get equal 0, you see how many times you added. If you get P, that means characteristic P. If you add 1 plus 1 plus 1 plus 1 and you never get 0, then you say that it has characteristic 0. So also, if you don't remember that, please look it up. So the rationals, the reals, they are fields of characteristic 0. 1 plus 1 plus 1 is never 0. But if you look at the integers mod P, so ZP, 1 plus 1 plus 1 plus 1 P times, you get P, which is equal to 0, right? So that has characteristic P. It's always important to look at examples when you see new definitions. And okay, well, vocabulary of rings, this is what you expect. Okay, it says that it's an elementary class, meaning it has a set of axiomatization. I remember elementary means of any size, Formiletti, but not strong, so it cannot be a finite set. And this is because he probably used an example before about this. That if we let sigma be the conjunction of the field axioms, so like those, I don't know, 9, 10 axioms for field, and we let tau n be the sentence 1 plus 1 plus 1 plus 1 different than 0, where there are n many ones, so meaning n here, for each n in the natural numbers, positive natural numbers, then the models of all these sigma, where sigma contains these formulas, little sigma and all the taus, are exactly K. Okay, so capital sigma is axioms of fields, and all these taus right here, the models of that is exactly K. Doesn't make sense? Yeah, because K is a set of fields, that's sigma, of characteristic 0. That's all the taus. Remember, characteristic 0 means that it doesn't matter how many times you add 1, you never get 0. Assume that K is a strong elementary class. And why do we assume that? Well, because we are trying to show that it's not a strong elementary class, so we're going to use contradiction. By proposition 6.3.7, meaning this one we just read, we may fix a finite subset of sigma such that K, the fields of finite of characteristic 0, are exactly the models of sigma 0. And then you can just read this again and see that's exactly what it says. So if you're strongly elementary in the models of sigma, you can choose a subset, so you have the models. And if you have a subset, you can fix an n such that sigma 0 is a subset of, well, this one may contain or not. And a finite subset of this guy will just contain tau n up to some point, capital N. Okay, so that makes sense. And so what do we do next? Now fix a prime p larger than n, which is possible because there are infinitely many primes. We see that Cp, so this means integers modulo p, which again you might need to look that up, is a field, and it has characteristic p, 1 plus 1 plus 1 p times u back to 0. It's a model of sigma 0. Why is that? Well, because it's a field, it satisfies this, and 1 plus 1 plus 1, if you add them less than n times, you still don't reach n, because p is bigger than n, and you have to go out to p to go back. Okay, so this is true, it's a model of sigma 0. And it's not an element of K, well, because it has characteristic p and not 0. Okay, so that's why. So this is a contradiction because we say that all the models of sigma 0 are exactly the ones in K, and then Zp is a model of sigma 0 but not in K. This is a contradiction, so which comes from where? So K is not a strongly elementary class, so the contradiction comes from the assumption that K was a strongly elementary class. So there you go. That's how you apply proposition 6.3.7. See you guys later.